Today we have Dr. Andrei Pavelescu from the University of South Alabama. And I hope you can see the title of the talk on your screen because he's sharing his screen. And this is the third talk on the Trojan Math Seminar and the second talk from South Alabama. Okay, Andrei, so I think it's your time.
Okay, thank you very much. Thank you for the invite and for being able to speak in this novel environment. This is a joint work with Dr. Ramin Naimi from Occidental College and Dr. Elena Pavelescu from South Alabama again. So yes, we are invading, we're taking over South Alabama people. Before I start, this was supposed to be, I mean, it is a sort of a general audience talk, so I'm going to start slow but get into high gear really fast. And one convention is this: anything that's in black, it's a known or proven result. Anything that's red is up for grabs. I wanted this to be a, if you're interested in this talk, there are some open questions sprinkled throughout the talk. So, and by the way, I don't know, I mean, I never timed this, so it could be long, it could be short, but don't hesitate to interrupt me and ask me questions during the talk. Okay, so quickly, I'm talking about graphs, but not very complicated ones, just simple graphs, meaning you don't have any double edges, you don't have any loops. So in between two vertices, you either have an edge or you don't. Okay, so standard notations, I'm going to label the graphs, the vertices of the graphs either through numbers through 1 through n, or vertices indexed by 1 through n. The size, the cardinality of the vertex set is called the order of the graph, and the number of edges or the size of the edge set is called the size of the graph. So these are some standard conventions for notation. Okay, Kn will denote the complete graph on n vertices, and those are the pictures of all the complete graphs up to order 5. Now just a combinatorial counting argument tells you that the size of the complete graph is n choose 2, so therefore n times n minus 1 over 2. What you need to remember from this, it's roughly of the order of n squared. Okay, if you are given a graph G, then I'll let C of G denote the complement of G in K of n. What does that mean? It means it's a graph which has exactly the same vertex set, but it has the mirror image of the edges. Wherever you had edges, you don't have them anymore, and whenever you didn't have, you have those. So basically, the edge set of the complement and the edge set of the graph form a partition of the entire edge set of the complete graph, right? Put them together, they overlap perfectly. Okay, so here's a picture. If you look at the graph on the left, the complement of it in K5 is just the graph on the right, basically telling you that the original graph is only missing 2 edges in order to be a complete graph, the edge 1, 3, and the edge 2 to 4. Okay, really important notion in all the results that are about to come is that of a minor of a graph. Okay, so what's a graph minor? It's not really a subgraph, though it could be. A graph minor is any graph that you can obtain from the original graph by doing one of 3 operations: vertex deletion, edge deletion, and a simple edge contraction. So here are the pictures. Let me spend some time talking about them. So if you look at this graph G, if you erase the one vertex, of course you erase any edge that's incident to it. So if you erase the vertex 1, the vertex 5, you get this graph. Or basically a 4th cycle here. If you erase an edge, it's exactly what the name says. You erase the edge and you get the original graph minus that edge. So if you erase from this graph, you erase the edge 2, 3, you get this graph over here. And the most important operation you can do for minors, in my opinion, is the simple edge contraction, which means you identify an edge. So we're looking at the edge 2, 3. We're identifying the endpoints, but what happens when you overlap 2 and 3? You might create double edges. For instance, 2 was connected to 5, 3 was connected to 5. So when you identify 2 and 3, you might get a double edge from the new vertex to 5. Well, you erase any double edges thus created. So if you do a simple edge contractions from contracting the edge 2, 3, you get a minor, which notice is not a subgraph. This or the original graph contained no complete graph on 4 vertex. So a minor is not necessarily a subgraph, but if you agreed to make this convention that whenever you identify, when you contract an edge, you relabel the newly formed vertex by one of the previous existing labels. At least the vertex set is a subset of the original vertex set. So minors are not necessarily subgraphs, but yeah, they are smaller, and you can reindex them to be such that their vertex set is a subset of the vertex set of the original graph. Okay, but what's really important about taking minors, it's really useful in what I'm about to say about the results that are going to follow, is what happens in the complement when you do a minor, and especially when you do an edge contraction. So if you look at this graph on the left, the graph on 5 vertices here, and you contract the edge 1, 2, you obtain this graph. It's a minor of the original graph. And in the complement, what you obtain is always a subgraph. This is really important. Contracting one edge in a graph creates a subgraph in the complement, which is also a minor. Okay, so I'm going to come back to this later on. And then minors are really important because of a very, 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 very important theorem in structural graph theory. It's actually a series of 23 papers spanned from 83 to 2004 by Niels Robertson and Paul Seymour, which says that every graph closed under taking minors, every class of graph closed under taking minors can be defined by a finite set of forbidden minors. What does that mean? It means if you have some class of graphs such that the minute you have a graph, you also have all of its minors in the same class, then you can describe this class by a set of forbidden graphs, meaning, let me give you an example. Okay, so look, a graph is a linear forest. It's basically a disjoint union of paths, of simple paths, no loops, no nothing. And the set of forbidden minors is made up by the complete graph on 3 vertices and the claw graph, the bipartite graph K3-1. So this is telling you, if somebody gives you a graph and they ask you, is this a disjoint union of paths? You can basically check whether it has a K3 or K3-1 minor, and if it doesn't, then yes, the answer is yes. If it has one of these as a minor, then it can't be there, right? This is what I mean by forbidden minors. It's kind of a politically incorrect criterion. You judge a parent by its offsprings, right? If the minors are bad, then you can't be in the set. So anyway, the next example, a graph is outer planar if and only if it does not have either of K4 and or K23 as a minor. A graph is called outer planar if you can draw it in the plane such that all vertices lie on one of the faces. Okay, and I want you to see a pattern here, K3, K3-1, K4, K3-2. The really important statement is comes from Wagner and also Kuratowski around the same time. They show that a graph is planar if and only if it does not have either K5 or K33 as a minor. A graph is planar if you can draw it in the plane without any edge intersections. That's one definition, but also another definition would be a graph is planar if and only if it doesn't have either of these two as a minor. Okay, so another way of phrasing this, the set of forbidden minors for the property of planarity is K5 and K33. Now, if you see the pattern here, K3, K3-1, K4, K3-2, K5, K3-3, it's only natural to ask the following question. So basically, you can reverse engineer this topic and ask, okay, I'll give you a set of graphs. Okay, for finite set of graphs. Can you come up with the topological properties of graphs for which this set is the set of forbidden minors? So can you ask the reverse question? And in 2017, Vaidi Sivaraman, he's in Mississippi now, he asked this question. Okay, if you look at K6 and K3-4, so following this pattern, what topological property is described by this set of forbidden minors? And remember our convention, black is known fact, red is conjecture. Then what the heck is purple? So this was a conjecture, we believed it was a conjecture, but apparently there is a graph, there is a paper out there which claims to have a solution. Problem is they don't really do any proofs. But if you check it, it says that the topological property defined by this set of forbidden minors is, if I'm not mistaken, it's something called two-paneled. But okay, this was just an example of what kind of questions you can do playing with the Seymour, with the Robertson-Seymour theorem. Okay, but to the main point of this talk. Okay, in 1962, so what is this, 38 plus, almost 60 years ago, battled Harary and Kodama, and I think at the same time, Tutte, and one other guy that I can't remember, proved the following theorem. If you take a planar graph and of order 9, and you look at this complement, that complement cannot be planar. They did a topological proof. I think Tutte ran a computer and checked this, but this is the result that is motivating the entire talk today. The complement of any planar graph of order 9 is not planar. Another way of saying this fact is K9 is not biplanar. In other words, K9 cannot be decomposed into a graph and its complements such that both of them are planar. So that's another way of saying this result. And this result is the best you can do, because if you look at the black graphs here, they are complements to each other. They have order 8 and they are both planar, thus showing that K8 is biplanar. You can decompose the complete graph on 8 vertices into 2 planar parts. However, Harary and Kodama's result claims that you can't do it from 9 on. K9 and therefore K10 and so on are not biplanar. Okay, so this is 60 years ago. People looked at it. Somebody recently, I think 2020, came up with a new proof for this fact. So the question is, how can you generalize this result? So there are 2 ways you can do this generalization. If you think of a property, so being planar is a hereditary property, meaning it's closed under taking minors. The minor of any planar graph is planar. So if you start with another, you replace the word planar with any other minor closed property. What is the smallest order such that Kn is not by that property? So for instance, you could ask, what's the smallest n such that Kn is not by outer planar? And the answer would be 7 in that case situation. But we're going to study more complicated classes of graphs and answer this question, hopefully. And another question is, okay, if you take a planar graph of a fixed order, what kind of topological property does its complement have? So if you fix an order and you look at all the planar graphs of that order and you look at their complements, do the complements share a common property? And if so, what is that common property? So the talk is basically split in 2. Questions of the first type and questions of the second type. It's mostly questions of the first type. Are there any questions so far before I start with the actual results? Okay, I'll move on. So in some sense, the first logical step up from being planar is being apex. So for a fixed integer t, a graph is called t-apex if you can find t vertices which removed produce a planar graph. So for instance, a 0 apex graph is a planar graph, meaning the graph was already planar to begin with. And 1 apex graph is simply called in literature apex. So what's an apex graph? It's a graph that might not be planar, could be planar, that's not a problem, but might not be planar. But once there is a vertex which you can remove and that graph becomes planar. The subgraph you get is planar. So here is an example. This graph is not planar because I think if I'm not wrong, you can do 2 contractions and create a K5, and that's a forbidden minor for planarity. But if you remove the top vertex, the indexed by V there, obviously you get a planar graph because look, it's drawn and it's planar, no intersections. So this is one class of graphs, and it's hereditary, meaning the minor of any one apex graph, the minor of any apex graph is apex, the minor of any t-apex graph is t-apex. Okay, so remember the first type of question. So for what order is Kn not by t-apex? And in 2018, Thomas Matman and I forgot Ken Ichihara proved that for all t greater or equal to 0, K2t plus 9 is not by t-apex. So for instance, K11 is not by apex. K13 is not by 2-apex, and so on. It goes in odd numbers. So they proved this, but the question still remains, are these the best bound? Are these the lower bounds where this happens? And not well, very soon after this result, myself and Elena proved the following result, that K2T plus 8 is bi-T apex, thus showing that Madman's and Ichihara's bound is tight. It's the best you can do. Okay, and here are some examples. There's nothing like reusing a picture from the same talk. You've seen this picture before, but now if you look at the graphs, including the red vertices, so what this symbol means, if you look at the left graph, it means you have the graph in black, it's the planar part, and then you fully cone over every vertex from 1 to 8 with another vertex 9, and then you have a vertex V10 lying about. That graph is obviously apex. If you erase V9, you get a planar graph. You get the black graph and isolated point V10. The complement of this graph is the graph on the right, which is also apex, because if you erase V10, you get the planar graph in black and isolated vertex V9. So this is an example which shows that K10 is bi-apex, for instance. And then this graph right here, it's a graph on 12 vertices. It has, what, 33 edges, if I'm not mistaken. It's a self-complementary graph, but this is 2 apex. If you erase this vertex and this vertex, you get a planar graph. One can check. And obviously, the complement is also 2 apex because the complement is isomorphic. This is a self-complementary graph. So this is the example that shows that K12 is bi-2 apex. And based on self-complementary graphs, I mean, we provided a full class of examples in even order showing that those are bi-T apex, and they are constructed on self-complementary graphs. Okay, so that fully answers the question of P property for T apex graphs. Okay, the next step over, we're getting stuff into more complicated stuff, is the notion of a linklessly embeddable graph. So first of all, a graph is called intrinsically linked if every one of its embeddings contains a non-trivial link. You have 2 cycles such that the edge of one pierces any disk that So a graph is called intrinsically linked if there is no embedding where you don't have one of these non-trivial links. Can you still see me? I have a report that bad network quality.
Yeah, we still hear you and see you.
We see you.
Okay. So a graph that is not intrinsically linked is called linklessly embeddable. It means it has an embedding where you don't have any non-trivial links. Okay. And this is a hereditary property. It means, again, by the Robertson and Seymour theorem, that this class is fully described by a set of forbidden minors, and these are fully known due to a paper by Robertson, Seymour, and Robin Thomas, in 1993. Graph is nil only if it doesn't contain any of the Peterson family of graphs as a minor. And this is the picture here. You start with the smallest one is a complete graph on 6 vertices, it's K6. And the last one is a 3-connected intrinsically linked graph that's called the Peterson graph. So the entire family is called the Peterson family after that graph. Okay. I should have said before that even though apex graphs are kind of simpler, we don't know. I mean, to my knowledge, the class of forbidden minors for apex graphs is not known. So that's something that one should research and provide a list. It's finite, but we don't know what it is. So that's an interesting question. But for linklessly embeddable graphs, we know the set of forbidden minors. There are just 7 of them, and here they are. This is from Wikipedia, I think. Okay, and one other thing to notice is that every apex graph is nil. It's not really hard to come up with a linkless embedding of an apex graph. Once you come up with a planar embedding for the planar part, you just cone over it to the apex, and that has no chance of creating any linkage. But we can prove this result using a tool that is going to be introduced later on in the talk. But also, if you think about the logic of it, if the class of apex graphs is included in the class of linklessly embeddable graphs, then the class of forbidden minors, the set of forbidden minors for apex graphs, must contain the set of forbidden minors for the linklessly embeddable graph. So you know where to start. You start with those 7 and you add some more. Okay. However, the classes are not perfect overlap, and this is an example which shows you that you have linklessly embeddable graphs that are not apex. This is called the Jorgensen graph. It's been introduced in a paper in 1989 by Leif Jorgensen. It's basically the graph you saw before with an extra cone added on the planar part. So this is, if you raise the top and the bottom vertices, you get a planar part, but there's no one vertex that you can erase and get a planar graph. So this is not one apex, but it is two apex. Okay. So again, coming back to the question, for what order do you, what is the smallest, the minimal order such that Kn is not bi-nil? So how would you approach such a question? Well, there's a very important tool from 1968 due to Wolfgang Mader. He proved that any graph on n vertex, he proved way more, but for our intents and purposes, any graph on n vertices and at least 4n-9 edges contains a K6 minor. This is telling you that if you have a large enough size in your graph, you are guaranteed to have a K6 minor, and then since that's a forbidden minor for linkless embeddable property, then your graph will be intrinsically linked. And this is pretty useful if you think of what it's saying, large enough, but look, the bound is linear, it's 4n-9. If you remember, the complete graph has n times n-1/2 edges, meaning it's growing as n grows larger, that thing grows quadratic. So at some point, it's n squared, anything of the order of n squared is bound to be twice as big as 4n-9. So just by using Mader, it's guaranteed that at some point, if you look at a large enough Kn, one of the graphs has to be bigger than 4n, has to have more than 4n-9 edges. And the point is, you don't have to go very far if you just do basic algebra. So if you impose this condition that the size of the complete graph should be bigger than 2 times 4n-9, thus guaranteeing that one of the graph or its complement has at least 4n-9 edges, turns out that n greater or equal to 15 works. So just using the Mader bound, it's guaranteed that Kn is not bi-nil for any n greater or equal to 15. Okay, so when you're hunting for the lower bound where this happens, it has to be somewhere between 11 and 14. Remember, we did show that K10 is bi-apex and therefore bi-nil. So what is the true value? This was a question that tormented myself, and I suspect Elena too, for quite a while. So in 2019, so last year, well, that's when it was published. Anyway, we proved that if you have a simple graph on 13 vertices, then either G or the complement is intrinsically linked, thus showing K13 is it's not bi-nil. But the question is this the best bound possible? It still was an open question whether 12 or 11 could be the best bound. And again, purple. What does purple mean? This is a done deal. We have to write it up. We check this together with Ramin, our collaborator from Occidental, and my student, Ryan. I think he's on. I can't see him, but anyway. We will prove that the true bound is 11. So K11 is not bi-nil. And this is the best you can do because K10 is bi-nil. Okay. This has been done partly with the use of computers. We use the Alabama supercomputer to check some of the cases. But I mean, we cut the problem if you tried. So it was a daunting task even using a computer because it's in the order of billions of graphs that you need to check if you just do it blindly. But then we use some math theorems and lemmas, and we cut down the order to tens of millions. And then we could partition the problem and use the supercomputer. Okay, so that's the nil part, the intrinsic link. And the last topological property I want to talk, it's of very interest to math biology. It's of high interest to math biology. It's intrinsically knotted. So let me just, what's a knot? Well, it's an embedding of S1 into the three-dimensional space, which cannot be homomorph, isotope, whatever you want, to a simple circle. You can't unknot it without cutting it, basically. And here's an example. I didn't want the classical one is the trefoil knot. I wanted something more complicated. This is a knot with 5 intersections in the simple presentation. Okay, so now if you imagine a graph, when you imagine a graph, you know it's a piecewise linear. If you think about, you take a cycle, that's a piecewise linear embedding of S1, right? It's a closed curve. Question is, sometimes it can be a simple one where that actually bounds at this, but sometimes it has self-intersection, not self-intersection on edges, but one of the edge pierces any disk you would try to have bound your cycle. So this is what I mean by a knot in a graph. And now a graph is called intrinsically knotted if every embedding contains a non-trivial knot, and knot that is not isotopic equivalent or homomorphic to S1. If a graph has a knotless embedding, then we call that not intrinsically knotted. So same question as before. What is the lowest order such that Kn is not bi-unique? So this is a very, very hard question for many reasons. One of the reasons is we don't know the set of forbidden minors for Nick. And not only that, in 2011, Thomas Mattman and Ramin Naimi produced over 200 forbidden minors for this class. But the class is by no means complete, and there are some people who claim to have over 400 of them. So, you know, the Robertson-Seymour theorem says it's a finite class, but it's a finite set. What finite means, well, if it's 1,000, then we're not nearly there with 400. But the graphs that are most, amenable to proofs and that pop up in many, many instances are graphs derived from these two, either the complete graph on 7 vertices or the 4-partite graph K3311. I think, colors here encode the partitions. Okay, these are intrinsically knotted. This you can prove by hand. And then what you can do, you can perform delta Y moves on them, and you still would get intrinsically knotted graphs. What does delta Y move mean? You look at the triangle, you take any triangle in your graph, so a full cycle, a full 3 cycle, you erase its edges, and then you add a common neighbor to those three vertices. So you erase the edges, and you put a new common neighbor. So you're basically creating vertices of degree 3 at each step. At some point, the process ends because you're running out of triangles, right? You're destroying triangles. You will be left with without triangles. So this process will stop. So I think so. If you start with the graph and you do these operations, I think these are called cousins of the original graph. For some reason, I keep saying cousin, the French word, but anyway. Okay, so we don't know the forbidden minors for intrinsically knotted. And I'm going to tell you later on why intrinsically knotted is still very, very hard. But if you had to guess, look, K9 is not bi-planar. K11 is not bi-nil. What would you guess is the bound for not bi-unique? So, okay, so this is, remember, red is up for grabs. Find all the minor minimal intrinsically knotted graphs. There are some brute force algorithms out there that sift some of them, but no algorithm is guaranteed to find all of them. So if you can come up with some math reason for why your algorithm will completely determine the graphs, it doesn't matter how long it runs, it will be meaningful. Of course, if you can build them by hand, but if you can build more than 500 graphs by hand, that's really impressive. Please talk to me if you can do that. Please let me know. Okay, so this is in preparation. It's almost a preprint. It's going to hit the archive pretty soon. We can prove that K17 is not bi-unique. And this is the first result of this type for intrinsically knotted, but we suspect it's nowhere near the actual bound. So here's the conjecture up for grabs. We suspect that 13 is the lower bound. So basically, it all behaves nicely. It jumps in odd order. K9 is not bi-planar, K11 is not bi-nil, and we suspect that K13 is not bi-unique. But without the set of forbidden minors or some clever argument, this is a very, very hard question. Okay. So let's switch to the second type of. Are there any questions here? Okay. Yes? No? Okay. If not, I'm going to switch briefly to the second type of question. The second type of question is, if you take a planar graph, what can you say about its complement? So again, revisiting this result, in 62, we know that the complement of a planar graph of order 9 is not planar. In 1996, Kotlov, Lovash, and Vempala, they prove other results that I'm going to talk in a brief moment, but right now, one of the corollary of their results is that the complement of a planar graph of order 10 is intrinsically linked. Okay, and then it's coming out soon. This result, the complement of a planar graph of order 11 is EK, intrinsically knotted. So one of the things is, okay, what's the same? What is the result for 12? What can you say? How bad or how ugly or how twisted are the complements of all the planar graphs of order 12? We don't have a topological property to put in there. I mean, we can think of ugly properties that imply intrinsically knotted, but it's not known. That's up for grabs, right? So if you look at order 12 or higher, and you look at the class of planar graphs and you look at their complements, they will be at least intrinsically knotted, but so probably from 12 on, they're even more twisted than that. But what do I mean by more twisted? That's for topologists to define. Okay, and how? Okay, so now here's, I'm going to, the last part of the talk is talking about the tool that, one of the useful tools improving either type of results, the bi property the result or complements of planar graphs. So in 1987, Colin de Verdier, he was looking for another way of classifying planar graphs. Planar graphs were all the hype back then. And he came up with an algebraic invariant which quantifies the planarity of a graph. So it's a kind of a complicated way to define, but doesn't really, it's not that complicated. If you take a graph and you look at all the matrices, okay, you start with the adjacent matrix, and now you build an infinite class of matrices Mij with the following property. Whenever you have two adjacent vertices, then the corresponding entry in this matrix, you just put a negative entry, random negative entry. Okay, and you put zeros where you don't have adjacency. M has to have exactly one negative eigenvalue with multiplicity 1. And the very technical property, there's no non-zero matrix such that the product of your matrix with it is 0 whenever, and the entries in the variable matrix Xi are 0 whenever you are on the main diagonal, or whenever Mij is non-zero. It's a technical property which makes it really, really hard to compute, calling the Verdier invariant. But to rephrase, what you do is you build an infinite set of weighted adjacency matrix for the graph, right? Basically, whenever you have adjacency, you put negative numbers, random there. On the diagonal, you don't care, you can put anything. And then you have to satisfy two more technical conditions. So technically, you come up with an infinite set of matrices, then the Verdier invariant associated to the graph is the largest corank, is the maximum on the coranks of these matrices. So how do you compute the maximum of an infinite set? So in practice, this is really, really, really hard to compute. If I give you a random graph right now on 6 vertices, computing its the Verdier invariant is kind of hard. However, there are, just using linear algebra, there are some things that one can compute. So first of all, there's a very important property of this invariant, meaning it's minor monotone. If you have a minor of a graph, then the mu of the minor is less or equal than the mu of the graph. This is really useful, really, really useful, because, and then simple computations show that the Verdier invariant of the complete graph is n-1 from K2 and on, and the complete the Verdier invariant of the empty graph, so the complement of the complete graph is the empty graph, the graph with all vertices but no edges is 1. But what makes it really useful for the type of questions I presented before is the following thing. Mu, so remember, De Verdier invented mu to quantify planar graphs, but it turns out that it quantifies way more topological properties than planarity. So mu is less or equal to 1 if and only if the graph is a disjoint union of paths, like a linear forest, as we said before. Mu less or equal to 2 if and only if G is outer planar. Mu is less or equal to 3 if and only if G is planar. This is what Colin de Verdier set out to do to begin with. But then really surprisingly, and this is due to Lobash and Vempala and Van der Holst, I think also, and of course Robertson and Seymour and Thomas, that mu is less or equal to 4 if and only if the graph is linklessly embeddable. So if you somehow can derive about a graph that its mu its mu is less or equal to 4, then you know it's linklessly embeddable without having to check whether it has one of the forbidden minors as a minor. Which I should say, by the way, so even if you have a class that for which you fully know the set of forbidden minors, finding out whether a graph is a minor of another graph is not an easy problem. It's a if you want to design an algorithm to check whether a graph is a minor of another graph, that's an NP complete problem. However, if you have a fixed minor for which you want to check, if you have case 6, designing an algorithm to check whether a given input graph has a K6 as a minor, that's a polynomial time algorithm. So it's sort of doable. This is what my student has been doing with the supercomputer, checking for K6 minors. Okay, so this is another way of checking for linkless embeddability of a graph, though it's not very, it's still cumbersome because it's really hard to compute the mu. However, open question, really, really important, really, really important. If you do this, you will save a lot of time and it will have a lot of consequences. Classify the graphs that have mu less or equal to 5. There's a 2006 conjecture by van der Holst, which claims to produce the set of forbidden minors. Look it up, van der Holst. You can prove that conjecture. It will be really useful for the structural graph theory. Okay, and another reason why mu is really useful, that it doesn't just play well, it's not just minor monotone, it doesn't just classify topological properties of graphs, but it also plays well with topological properties of the complement. One other property it has is this: if you take a graph, so think of the planar graph here, and you add one vertex, doesn't have to be cone here, the add vertex connects to everything, it doesn't have to connect to everything. So if you add one vertex to a graph, the mu can go up by at most 1. And if that new vertex connects to every previously existing vertex, the mu actually goes up by 1. That's a proven fact. And then, as I claim, mu plays well with complements. So if you have a G as a disjoint union of paths, so meaning it's really sparse, right? A disjoint union of paths is kind of very rare. Then it tells you that mu of the complement is really high. It's n-3. Remember, mu of the complete graph is n-1. So if you have a disjoint union of paths, then the complement of that has a really high mu. If you have an outer planar graph, then the complement has mu greater or equal to n-4, still really high. And if a graph is planar, then the complement has mu greater or equal to n-5. And this is where I claim that Vempala and Lovash prove the following result. Okay, think of what happens. What does this statement say if you have a planar graph of order 10? If you have a planar graph of order 10, then the mu of the complement is greater or equal to 5, 10 minus 5, right? So if it's greater or equal than 10 minus 5, it can't be linklessly embeddable. So this is the result. If you have a planar graph of order 10 using the mu, then the complement has to be intrinsically linked. Okay. However, this gives you nothing about. So one open question is, if G is linklessly embeddable, what can you say about its complement? This is not known. We don't know anything about this. Again, this would be really useful. And also, here is, remember when I said that intrinsically knotted graphs don't play nice with others? Well, there's no real connection between mu and the intrinsic knotted property. We don't know. There's no result that says if mu is large enough, then you have an intrinsically knotted graph, or a result that says every intrinsically knotted graph has a mu at least something. Well, it has a mu at least 5 because intrinsically knotted implies intrinsically linked. However, there is a conjecture out there which says that if you look at a graph and you look at its complement and you take the mu of both, then the sum is at least n-2. So that's out there. But for intrinsically knotted, there's nothing you can say. And here are some examples that show the following fact. So in 2003, Joel Fouissy built an example of an intrinsically knotted graph which has mu very low, mu equals 5. On the other hand, there are examples of not intrinsically knotted graphs which have mu equals 6. So mu equals 6 does not guarantee intrinsically knotted. One can conjecture, but it's such a risky conjecture that I didn't even write it down, that mu greater or equal to 7 would imply intrinsically knotted. So I'm not writing it down, but if it's true and you prove it, cite me. Okay, for this conjecture. But if you're willing to play without a mu, you can still prove results. If you're willing to do combinatorial arguments, you can still show, for instance, that the complement of a linklessly embeddable graph of order 14 is intrinsically knotted. We conjecture that you can actually lower it down to 12, but there is no proof for that factor yet. Okay, and I think that's all.
Thank you very much, Andrei. Do you have any questions for our speaker? I have some graph theorists in here. Dr. Voloshin, are you there?
Don't put them on the spot.
Yeah, I don't see anything. I have a couple of questions regarding. I heard the word supercomputer in Alabama several times. So you solve some problems using the computer, right? Where's that? And how do you use that?
Not really, not yet. We checked some. We proved something by hand, but at the same time, when we were working, we checked with the supercomputer. What the supercomputer is going to help us is fully prove that statement about K11 being binil. That will have some computer part into it.
Okay.
But for instance, I worked with some of the students who were present here on Jorgensen conjecture type questions, and we checked some of the results by the computer. So I knew them to be true before we proved them by hand, which was kind of useful. It's easier to prove something when you know it will eventually work out.
Mm-hmm. Yeah, I'm not a graph theorist, but you know, between graphs and matrices, there's very good, very tight relation. Because each graph.
Verdier is a linear. It's
my question regarding this relation, like, because you talk a lot about graph and minors, and then several properties of graphs, right? Topological properties. So I just wonder if there are some corresponding properties for matrices or not. Like, sometimes we can use matrix language, right, to solve the problem.
What I can tell you, it's fully encoded in this calling the Verdier matrices. Though all the connections, I mean, you can't do any better than this. All the connections are in understanding how to actually compute the calling the Verdier. It's the co-rank of matrices. This is how it's defined. You take the graph, you build weighted adjacency matrices corresponding to the graph, and that's where you encode the topological property from the graph in this weighted adjacency matrices. But now you have matrices, you don't have anything else. The task is finding the maximal co-rank of this infinite set. And all the proofs I've seen, because mostly they're done by topologists, not by linear algebra specialists, are this. They guess what the answer should be. They find one example in that infinite set where the maximum is attained, and then they use some topological arguments or some linear algebra arguments to show you can't do any better. But it's all lies into guessing, knowing the answer before you prove it, basically, or suspecting what the answer is. So if there is a really good way, if somebody could come up with a really good way of computing this mu for any graph, then you would just churn out papers about structural graph theory with this invariant. But it's kind of a cumbersome definition.
Okay. Do you have anything else for Dr. Pavelescu? All right, so I don't hear anything else. Yeah, thank you very much, Andrei. So for interesting talk.
Sure.
Yeah, and using this case, I just want to announce that we will have a seminar next Thursday. I will send out an announcement about it, like detail, time, and title, and abstract. Okay. Yeah. Thank you so much.
Yeah.
Thank you.
Yeah. Thanks. Thank you for joining us.